Okay, so welcome everyone. Today we are going to have a second lecture in the course. We're going to continue our discussion of models with constraints. If last time we discussed like very basic idea of differential algebraic equation, right, as a something in a way different from ordinary differential equation, we saw that those are in a way similar, right? They're different, but in a way they're similar. The similarity came when we discussed normal form of ODE versus general form of ODE, right? General form of ODE and general form of differential algebraic equation, they appear to be quite similar to the point where it is hard to draw distinctions sometimes. Here, we're going to look into a concrete case, more particular case, that is mechanical equations with constraints. And you'll see a lot of similar dynamics, a lot of similar situations here. But at the same time, you would also see, all of this will become more concrete. All right. To start, I propose we go all the way to, original, you could say, original equation in the Lagrangian mechanics. Notice we could have started with Newtonian mechanics, but ultimately Lagrangian mechanics is a better start for us. Yes, is there any questions? Please speak up. Right. I mean, at any time, if you have questions, just speak. Okay. All right. So we will start with the Lagrangian equations. Is in a way is a better way to start. But we could have started with Newtonian as well. Okay, so let's just look first at what Lagrange equations look like. It is a familiar thing that you hopefully studied. That is equations of this form. What is written here is that a time derivative over a partial derivative of kinetic energy with respect to generalized velocities minus partial derivative of kinetic energy with respect to generalized coordinates is equal to generalized forces. That if you saw it for the first time, it would look random for you. It would be like, what is going on, why, etc. But there are good reasons why this is true. One good reason is you can derive it directly from Newtonian equations. So if you believe into Newtonian laws, then you could derive it directly from them. So there are derivations and they're not so difficult. Now, another way to say it is that there are various principles of optimality and so on that allow you to derive this. You could see it as an operator that acts on, kinetic energy. Like you take a function and you start doing things with it, like take it derivative with respect to the generalized coordinates, put minus sign, take time derivative with respect to the partial derivative of the first derivative, etc. Right? There are ways to different ways to look at it. But for us here, what is important is that we have this equation. And here, this describes the dynamics of a particular mechanical system. Okay. So we could use it to simulate the system, or we could use it to predict how it's going to behave in other ways. Important here is that kinetic energy, like this function, which we differentiate in various ways to work with this, kinetic energy has a form, like this is the form of the kinetic energy takes. it is the 1/2 of a quadratic form of this quadratic form. I mean, yeah, 1/2 times QHQ. Q are generalized velocities again. H here is a generalized inertia matrix. It is a symmetric and positive definite and full rank. That is properties that it has. It's a symmetric, not only symmetric, but also positive definite. And as positive definite matrix, it has full rank. All right. So that's what we have. That is what we have. Generalized coordinates, I would remind you, by definition, the set of coordinates, which is a minimal set, minimal in terms of number, that describes uniquely configuration of the system. Right? So system can have various configurations. So for example, if it is a two-link robot, it can have various ways those links can be oriented. And Q is a minimal set of parameters that describe each admissible configuration. Right. So for example, for a two-link robot with pin joints, it would have two general coordinates because two numbers are enough to describe any configuration of this robot. Basically, two joint angles is enough. For a rigid body in space, 6 parameters is enough to describe its configuration. So it will be 6 generalized coordinates. Even though there we have to worry about gimbal lock, but that is outside of our interest for now. Okay, for a rigid body on a plane, 3 parameters, 1 angle, 2 coordinates. Okay. So this is what vector generalized coordinates means. Generalized torques, that is what we're going to look at the second slide. All right. If you have any, any issues remembering this, I can assume that you studied it. That's why I'm only giving you like a very small discourse on it. If you have trouble with it, or if you didn't study it, please let me know or ask questions, and I would explain in more details. I can also provide you additional materials on how it's derived and so on. Okay. Now, generalized forces. Generalized forces, tau, can be generated by Cartesian forces or Cartesian torques. What I mean by Cartesian forces or Cartesian torques? Well, imagine you have, for example, a box that weighs 1 kilogram. You have gravity force acting on this box. The magnitude of this force is 9.81 newtons, right? Because box weighs 1 kilogram, so gravity force is mg, so g is 9.81. So you have 9.81 newtons acting on this box. Okay, I can even draw it for you, right? There's a box. Here's your force, 9.81. And you know the direction, right? Direction is down. If you want to write it in XYZ and your y-axis, let's say your z-axis is vertical, then the force would be like 0, 0, minus 9.81, right? So here we have a description of force. Notice it has 3 components. It has 3 components. That's and a force like this I would call it Cartesian. So it exists in Cartesian world, the world where we live, this 3-dimensional world, and it would have 3 components. On a plane, a Cartesian force would have 2 components, but we usually deal with spatial mechanisms, so we would encounter 3-component Cartesian forces usually. Now, what is a Cartesian torque? Well, it's typical torques that you saw in the classical mechanics course. So, for example, if this force is acting, on this box, but on the other hand, we have, for example, let's say a hinge here, right? Then relative to this hinge, we can compute what kind of torque it produces. We can notice that there is a distance certain distance between the hinge and the force, and this torque would be directed, in the plane, kind of like away from us, and so on and so forth. So the torque would also have 3 components. We could write it. Let's say if the hinge is a distance 1 meter away distance, then the torque would be, give me a second so I won't lie to you. It would be, let's say, 0, 9.81, 0, something like this, right? So my idea is to say that torques also exist in 3-dimensional space, and they're also 3-dimensional vectors. That's also why I call them Cartesian torques. Okay. So Cartesian forces, Cartesian torques are stuff that you studied in your, physics in high school, physics 1 in university, classical mechanics that wasn't Lagrangian mechanics, right? Like Newtonian mechanics, all of this. That is what I call Cartesian forces and torques. Okay, good. Now, those can generate generalized forces. For example, a relation between Cartesian force F and the associated generalized force can be described like this. You have generalized force tau I, which would be equal to this Jacobian times the Cartesian force Fi. Now here's a question. What is this Jacobian? Well, this Jacobian transposed, right? This Jacobian is, partial derivative of Ri, where Ri is a vector describing position of the point of application of force Fi. So if, for example, force Fi, here's a box, I'm drawing a box. Let's say, and here's a force, I'm drawing E force applied to it. So what we need is like description of this point with respect to origin, okay? With respect to the origin, but it has to be in terms of generalized coordinates. So we're not interested in how distant it is from the origin. We're interested in how this point is described as a function of generalized coordinates, because this point lies on the mechanism, so it can be described as a function of generalized coordinates. Since generalized coordinates describe any configuration of the robot, they can also describe any point on the robot. So any point of the robot can be described in terms of generalized coordinates as a function of generalized coordinates. That should be pretty familiar to you, right? For example, for a two-link robot, the end effector, like a point on the robot, can be described as cosine, phi1 L1 plus cosine phi2 L2, and that is like x coordinate of the end effector, or y coordinate would be like sines instead of cosines. Yeah. So yeah, we will see an example of this in a little bit. So don't worry if this sounds a little bit strange. We will see examples. Yep. So this is what we want here. Like Ri is the position of some point on the robot, on the mechanism, which is described as a function of generalized coordinates. And we take Jacobian of this point, so take a partial derivative. And that partial derivative transposed, notice, it is transposed here, is, if multiplied by Cartesian force, produces generalized force. This you should have seen in 2 courses. One in a course on classical mechanics, Lagrangian mechanics. And second time you should have seen it in Introduction to Robotics, where you worried about the question of torque control, where you're worried about or human robot interactions or compliance control, one of those things, where you were worried about what is the force produced by end effector of your robot, given torques, joint torques, or vice versa, what joint torques should produce a given given force. You saw their similar relation, some kind of Jacobian transposed like this, right? Hopefully you did that. Hopefully you saw that. Right. Okay. Now we can denote this Jacobian, dr dq, as gi. Okay. GIR. Sorry, I missed the R here. R here. GIR. Right. And what we have is that this generalized force can be found from Cartesian force by multiplying it by this Jacobian transposed. Okay, so this is very neat and handy notation. All right, now to generalize torques. Let's say we have a two Cartesian torques. So let's say we have a Cartesian torque M. Notice that bold are always vectors for me. So this bold M is a vector. You could complain that it looks a lot like a mass, but you cannot because bold, right? I would suggest you keep this convention in mind. This is a very common convention in robotics. Bold Latin letters indicate vectors if they're small letters. Capital letters indicate matrices. So it's a very common convention, very useful. Okay. So yeah, for Greek letters, by the way, you could also use bold. That is, sometimes people do that, but that is not as common. So that's why, for example, I here don't use bold on this tau, even though it is also a vector. Right. And on this omega here. Right. Conventions. Okay, so what about Cartesian torques? So if we have a Cartesian torque M, we can find associated generalized force like this. So again, this is a generalized force associated with this vector. And here we also have a Jacobian transposed multiplied by this torque. But what is this Jacobian? This is a partial derivative of omega I. What is omega I? Well, omega I is angular velocity of the body to which Cartesian torque is applied. So let's say you have a rigid body in space. Angular velocity of this rigid body would be omega. Or let's say you have end effector. Well, angular velocity of this entire end effector, not some point on end effector, but the entire end effector would be omega. Any rigid body have only one angular velocity. Angular velocity is a property of a rigid body, whereas velocity is a property of a single point. You cannot say velocity of a body. You can only say velocity of the center of mass of a body, for example, or velocity of a particular point on the end effector. But for angular velocity is common property of the whole body. So that is quite interesting and important to remember. All right. So torque is also applied to the whole body. You cannot apply torque to a point. You apply it to the entire body. That's also quite interesting. All right. Whereas force, for a force, a point, you could say a force is applied to a particular point on the body, and that is very meaningful. For a torque, it is not. For a torque, you have to say the torque is applied to the body. Doesn't matter in which part. It only matters in which body it is applied. Okay, so the relation is still like that. So now you have to find partial derivative of angular velocity. And another big difference is that partial derivative is now with respect to generalized velocities. Right? So before it was partial derivative with respect to generalized coordinates. Now it is with generalized velocities. So d omega dq dot, that is a new Jacobian. We can define it as this Jacobian, sub I with upper script omega, and it is d omega I d k dot. And then we have this exact same, you could say, in structure relation where you have tau I equal to Jacobian transposed times this time Cartesian torque. Previously it was Cartesian force. Now it is, subscript is omega. Before subscript was r, right? Position. Now it is angular velocity. Okay, so this is what we have. This is what we have. This is the relation between these quantities. Now, we could define what we call a range W. W. Notice this is not omega, it's W, different letter, and bold now because Latin letter. Okay, so W. W, call it sometimes. Right? So this is a range. Range is a concatenation of a force and a torque. Okay, so it has two entities concatenated together. Range is a 6-dimensional object. And we can define a relation between a range, W, and associated generalized force. And that is essentially just take two vectors, like two Jacobians, concatenated, transpose, multiplied by this range. Or here we just define one, we drop the subscript, so superscript, we drop it, and we get just one J sub I transposed times range. So if we have at the same time like a force and a torque acting, then we could define a range, and we could, concatenate those two Jacobians, and this works out. This works out. In practice, this happens sometimes. This happens sometimes when you have like a clear relation between a force and a torque, and they exist simultaneously and they somehow related to each other. And so it is more meaningful to talk about a range than about separately about torque and a force. So this you could write it this way, right? And the total generalized force can be computed then as a sum of all individual ones. So sum of all branches acting on the body, if you want. Notice that if you only have a force, you don't have a torque, you can still write as a range, you just have a 0 here, and vice versa, right? You could always put a 0 in front of a torque, and you could still write a force as a range. So this is a general formula. But yeah, of course, you could write it as a sum, two separate sums, sums for torques, sums for forces. Okay. So this is generalized forces. Any questions so far? Okay. Now, Lagrange equations with constraints has the following form. We have a familiar Lagrange equation here. So exact same as before. Now we have additions. We have this addition here. So some kind of Jacobian transpose times lambda. And we have this addition here. So this is called constraints. And this is called reaction forces. Lambda are reaction forces. That's what we call it. So let's try to understand. So first of all, we can think of lambda as concatenation of all reaction forces associated with constraints. So it is just a big vector that is concatenation of various smaller vectors. Okay. Okay. Now, let's imagine that lambda is a Cartesian vector, like a single integer vector, just for simplicity. Let's imagine that lambda is a single Cartesian vector. Then what we have here is looks a whole lot like a transformation from a Cartesian vector to a generalized force, right? Like it just looks like a transformation from that, like this is just a generalized force generated by lambda Cartesian vector. Okay. So the form that we observe here is not strange in the sense that it makes a whole lot of sense. And in fact, here dr dq, this looks a lot like, just by definition, kind of like the way we defined everything, it looks a whole lot like it is a force, Cartesian force, being transformed into a generalized force. But we don't specify what R here is. So in a sense, it could be also a torque transformed to a generalized force. So don't think of it as necessarily, absolutely, for sure, Jacobian that is associated with forces. It could be a Jacobian associated with torques. Okay. It all depends on what R is. Okay. So of course, yeah, you here you have derivative with respect to q, not q dot. That's also important. Okay. 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 Now, wait, no. Here, I think it is quite clear that what we see on this right-hand side is a generalized force associated with something like, let's say, Cartesian force. Now, this we already saw on the previous lecture as like algebraic constraint, right? Algebraic constraint. So there's some equation that is algebraic, not differential, and it just exists. You add it to the original equation. But on the other hand, one of the important properties of this equation is that it is not going to actually do anything. Like it's not going to influence, for example, solution of this pink equation unless there is something additional that makes sure that it can do so, right? Like the pink part is still the same as before. So how would this green part, how would it actually be satisfied? And this is what does the trick. Like those reaction forces, they change the dynamics of the equation of the system in such a way that the constraint equation is satisfied. Well, that's what's going on. So again, this green part is a generalized force, which is generated by a reaction force. You can think of it as a Cartesian reaction force that actually makes sure that the constraint is satisfied. All right. So this is how it works. And what is especially interesting here is that for it to work, you see what happens here? There is a Jacobian here of this very expression. So it is a constrained Jacobian. This is what we call a constrained Jacobian. Like this expression here is constrained Jacobian. This is a constraint, and this is a constrained Jacobian. And that is enough to make like all of this work. So just to give one example, like what could it all be? Imagine you have two-link robot in space, okay, in space. So here's a joint. Here are two link robot in space. Right. So both the links would have 3 degrees of freedom if planar mechanism, right? So 3 degrees of freedom. But since they are connected with a joint, the total degrees of freedom of the mechanism is actually only 4. Okay, so there's a 4 degree of freedom mechanism. You can think of it as like 3 degrees of freedom one joint has, and another one link has 3 degrees of freedom, and another one only 1. So rotation with respect to the previous one. Okay, if any of those calculations sound strange, that is a good sign that we need to revisit a little bit of Lagrange mechanics or introduction to robotics or something like this, because those are basic computations you have to be able to make. I would be happy to expound on it like after the lecture or right now if you want. Okay, so 4 degrees of freedom. But now imagine that suddenly we say that this link contacts the ground, and we say that it contacts the ground and it cannot move relative to the ground. It can still rotate relative to the ground, but the point of contact cannot move. It cannot move left or right, cannot move up or down. So it is as if there is a new joint. Okay. So this will be constrained. The position of this point would be r. R of q will be position of this point. It will be two equations that describe the position of this point. And the forces lambda that would make sure that everything stays put would be reaction forces that arise at this point. Okay, so there will be reaction forces, contact reaction forces, normal reaction, and friction force, right? And those two forces will be lambda. Okay, so this is a crude example that I could give you. Yep. So that is an example of what lambda is and what r is. Any questions? Okay, we'll move on. Now, here's a more concrete example, a little bit more concrete example. Let us consider a 3-link mechanism whose end effector is described as, end effector is this here I mean like a point at the very end of the robot. It is described as x position of the end effector is x sub e is equal to L1 cosine Q1 plus L2 cosine Q2 plus L3 cosine Q3. Okay, so is that is like length of the first link times the orientation of the first link plus length of the second link times the orientation and so on. And the exact same way we have vertical position of the end effector is equal to sum of those 3 things, right? L1 sinus Q1 plus L2 sinus Q2 and so on. All right. Then if end effector is attached to the ground at a point xe equal to 1 and ye equals to 0, so we attach it to the ground, and notice that I use this star here to indicate that we are talking about no longer equations that describe the position of end effector in the mechanism, but about the point of attachment, like where this link is attached, right? Then the constraints that impose this attachment would look like this. Right? And notice we have again same expression. Oops, sorry. We have same expression here. Okay, same exact expression here. But additionally, now we have this -1. Why -1? Well, because we want the position of xe here to be equal to the position of xe star here. So xe minus xe star should be equal to 0, and that's what I write. Right? And downstairs, we have, again, exact same description as above, but it is just equal to 0. Why? Well, because remember, our xe star is also equal to 0, right? So 11, equation 11 describes for us the way we can write constraints for Lagrange equation with constraints. That is how it looks like. All right? Questions? Okay. Now, in general, we can distinguish, and it is important for us to distinguish between constraints expression, okay, constraints expression, and a constraints value, okay. For example, if the k is an effector and is described by a radius vector rk equals to rk of q, right? This rk of q is a constraint expression, right? Well, let me color code a little bit. So constraint expression, this radius vector rk as rk of q, that is a constraint expression. On the other hand, if we affix this k at a particular value, rk star, that rk star would be a constraint value. Okay. So the difference is one is the formula that allows you to find this point if you know generalized coordinates. That is the constraint expression. The constraint value is the particular value this formula takes for a particular q. That is one way to say it. Or another way to say it, that is the value that we know it has to take because this point is constrained to take this value, right? So for example, if we're talking about the foot of a quadruped robot, we can say the foot is on the ground. So the height of the foot is 0. So the position, every point on the foot, its height is 0. So we can say that y coordinate for each point on the foot has to be equal to 0. So for each of those points, we could find the expression as a function of generalized coordinates that describes the robot. That will be expression. But the value would be 0. We know that all of those points stay on the ground, so it is 0. You understand? Now, constraints usually take form like the following form. It is the expression, right? Expression minus the value, and we say it is equal to 0. So we, this is a convention. We like the right-hand side of the constraints to be 0. So we write constraints in the way, something equals 0. Okay. And to achieve this, we shift everything to the left-hand side and we say constraint expression minus constraint value is equal to 0. We could have written it as a constraint expression equals to constraint value. Yeah, I don't think any of this would have made it more intelligible. I don't think it would be easier to read. It's just one of those things. You understand it, and then it becomes clear. Before you understand it, it's not going to be clear, no matter how you write it. So, yeah. So this is what it is. This is what it is. But note, constraint value does not influence constraint Jacobians. Okay, constraint Jacobians are not influenced by constraint value. So if you only need Jacobians, you don't need to know constraint value. You only need constraint expression. That is quite an important observation to make. Like, you don't need to know how high the leg of your robot is if all you need is a constraint Jacobian, right? That is counterintuitive in a sense. And but it shouldn't be. Like, first of all, if you know your configuration of your robot, that implies that you know constraint value. You just know it implicitly. Like if you know configuration of your robot, then you know what from constraint expression, just by substituting user, you get your constraint value. So constraint Jacobian, because there's a function of Q, if you evaluate it at some point, this process of evaluation already kind of contains all the information about constraint values that you could have wanted. But explicitly, you don't need constraint value, right? So that is quite interesting. That's quite interesting. All right. This is one of those things which I suspect for some of you will not be clear from the first try. So try to go back through it later. Try to think about it. Is quite critical to understand this. So this is going to be important for the rest of the course, more or less. It is not a deep phenomena. It is just a question of names, right? Okay. If you have any questions. Okay, I'll move on. Now, Lagrange equations are famous, especially since you studied them in the mechanical course. But if you had a robotics course, you notice that we prefer to work with what we call manipulator equations, which is the same equations as Lagrange equations. This is exactly the same one. But we explicitly write them in a matrix vector form. Like Lagrange equation, you can call them a partial differential equations if you want, even though it is a little bit strange to call them that. But after taking all the partial derivatives and the time derivatives, you will essentially arrive at this guy. And yeah, in this guy you have H is a generalized inertial matrix. Remember, it is a symmetric positive definite full rank matrix. We have C times Q dot, that is a generalized inertial force. So it Coriolis force, normal inertial force, like centrifugal, we call it sometimes. Yeah, those forces, right? And then G is generalized gravitational force. That is just convention. For us, this particular structure doesn't make a lot of sense. Like this C matrix here doesn't do anything for us. Taking G as a separate vector doesn't do anything for us. So for us, it is a little bit strange, this notation. But this is the convention, so we are going to use it. We could have replaced C, Q plus G as a single vector. That sometimes people do that. But I'm trying to stick to as conventional representation as possible just to make it cleaner. Right? But this form is very useful for people who do parameter identification, adaptive control, and so on. Even some trajectory planning methods. But for us, it's not very important or critical to have this form. Okay, good. So this is the co-manipulator equations. Now, manipulator equations with constraints, sort of default way to write it would be quite the same. It would be, here is the manipulator equations. Here we add the same as before, we add just this partial derivative, this Jacobian transpose times lambda. And here we have constraints. So same as with Lagrange equation. And that is a common theme. Constraints appear in quite the same way everywhere. So you can even, if you look up at it closely, you can even recognize that it reminds you a little bit of Lagrange multipliers from optimization if you had optimization course. And in fact, if we are lucky, we'll get to study this relation as well. Right. So in some traditions, we call them unknown variables here. I call them reaction forces, but we could also call them Lagrange multipliers. In the Russian textbook on Lagrange equations, you would always call them unknown parameters or Lagrange unknown parameters or Lagrange multipliers, something like this. So this is, in fact, what I call reaction forces, you can call Lagrange multipliers. All right. And somehow it makes sense, right, that in Lagrange mechanics, you will have Lagrange multipliers. Lagrange was definitely aware what he was doing with his mechanics. So this formulation, is quite it's quite natural to see connection between that and optimization. All right. So you see this is the same as Lagrange equations, but here we now have manipulator equation form instead of partial derivatives of Lagrange equations. Okay. Now we can define. Let me use different color. This Jacobian dr dq. As I said, it is a constrained Jacobian, right? Constrained Jacobian. And then equations take this even cleaner look. Like we have now this Jacobian transpose times lambda, and same constraints in the as a second equation. So good, right? Looks quite natural and so on. So no problems. This form already is like a canonical form, you could say. Like this is stuff that you are going to see in papers, textbooks, and so on. This is in a way the most, how should I put it? This is in a way the most general correct way to write Lagrange manipulator equations with constraints. The reason is that constraint is added here explicitly. Everywhere we are going to, as we are going forward, we are going to drop this explicit representation of R here, and instead we are going to see derivatives of R, which is not the same thing. But this is also equation 14 is something that is very hard to work with because of this R of Q equal to 0. So equation 14 is the most correct, but also hard to work with. So that is something to keep in mind. Okay. Let's move on. And here what we can do is we can differentiate this constraint. So R of Q, we can differentiate it. What do we mean by differentiating? Well, we have dr dq. Differentiate with respect to time, right? But I do this as a chain rule. So dr dq times dq dt. That is still equal to 0 because R of Q equal to 0, so dr R dot also equal to 0 for sure. All right, but notice that this part here is a Jacobian, right? dr dq is Jacobian, constraint Jacobian. Well, dq dt is just q dot. So you have Jacobian times q dot. Jacobian times q dot. And differentiating this one more time, we get this expression here. So how did we get this expression? First of all, this is a multiplication of two functions, right? So how do we differentiate multiple of two functions? Well, first we differentiate one, then we differentiate another. So here we differentiate q dot to get q double dot multiplied by q by g by j, sorry. And here we differentiate j, so it becomes j dot multiplied by q dot, not changed. So, a times b, the derivative is a dot times b plus b dot times a. Right. This is what we have here. But remember, it is vectors, so you cannot switch places of parts of a product. So there is that. Okay. So this is what we have. This is what we have. We have expression 17. So expression 17 is constraint equation differentiated twice. This is a absolutely canonical, extremely important equation. This equation, you can think about it in this way. It represents a constraint on accelerations. So generalized accelerations have to abide by this constraint. So they have to live according to this constraint. Q double dot cannot be something that does not adhere to this constraint. And that is quite interesting because you could think of differential equations in general. What differential equations tell you? They tell you, for example, manipulator equations tells you your Q double dot lives according to this, equation, right? And your Q dot will, its evolution will be determined by Q double dot, right? Q double dot is the derivative of Q dot. And Q lives according, its evolution lives according to the Q dot, right? But at any point of time, if you're going to, for example, integrate it or whatever, you think of Q and Q dot as given, whereas Q double dot is computed, right? So if I give you Q and Q dot, you can compute Q double dot. And then you, knowing Q double dot, you can understand what is the next Q dot and Q will be like. For example, Cauchy problem would have as initial conditions Q and Q dot, and Q double dot will be computed as initial Q double dot. Yet another way to say the same thing, I'm trying to say the same thing in like 3 different ways, is that Q double dot is like a vector field that exists over Q and Q dot, right? So yeah, it's like a vector field. You have a n-dimensional vector Q double dot that is associated with pairs of Q and Q dot. All right. More correct way would be, of course, to say that Q double dot and Q dot are vector field associated with coordinates Q and Q dot, but yeah, that becomes a little bit, esoteric, I guess. But yeah, right. So even in this expression, I'm sorry, by the way, if I just made your head spin and didn't give you any information. But in this expression, what we have is this Q double dot is an independent variable, you can say. And its behavior is determined by this, this constant Q dot times J dot, and by this matrix J, right? So in a sense, it is a linear equation with respect to Q double dot. And Q double dot will have a particular solution in this linear equation, and will have null space of solutions. Null space of solutions. So Q double dot will live inside this null space, and but now null space is a linear space, right? But since this is a you can say affine equation, it will be also this linear space would be shifted from the origin based on this factor. All right. We will we'll discuss it separately, so don't worry. I'm sorry if this was a premature discussion, and, if it was too abstract. All right. And in the exact same way, you can say that Q dot here has a constraint. So this is a constraint on velocities. Well, this equation basically tells you what velocities you can expect. In particular, it tells you that all velocities you can expect live in the null space of this Jacobian J. So this Jacobian J has a null space, and all velocities that you can expect would live inside this Jacobian. Notice also that this includes initial velocity. So your velocity in the initial point of time would have to lie in this Jacobian. And where I was saying that initial acceleration is a function of initial conditions, initial velocity is part of initial conditions, not a function. So the initial velocity of the system would have to agree with this constraints. So if you have a Cauchy problem, what you have been provided with better agree with this this constraint, Zach constraint 16, right? Same as your initial position better agree with your constraint R of Q equal to 0. All right. So now instead of one constraint, we have basically three constraints. We have a constraint on position R of Q equal to 0. We have constraint on velocities JQ dot equal to 0. And we have constraint on acceleration JQ double dot plus J dot Q dot equal to 0. So those are our three different constraints. Okay, good. Now, we could replace the our constraints on position here with our constraints on acceleration. And there is a good reason why. The same as in last lecture, what we want is essentially, you could say, differentiate the constraints as or, algebraic part of the differential algebraic equation as much as we can, so that it would acquire derivatives of the same order as our differential part of the differential equation. So we want this part to have Q double dots, basically. Like here we have Q double dots, and we want here to have Q double dots. So we differentiate it twice, and we achieve this. In a sense, you can say this is because the business of solving differential equations or the differential equations is the business of finding highest order derivatives and expressing them out. So we want a normal form, but we cannot express out our higher order derivatives before we understand what kind of constraints are imposed on them. And to find those constraints, we have to differentiate constraint equation until we get explicit expression for the constraints on the higher order derivatives. And that is what we got in 18. This is a constraint on accelerations, and we are happy. Now we can express. How do we express? So here we have we write the same thing, but in a matrix vector form. So this guy we have here, this guy we have here, but we transfer to the left hand side with a minus sign, right? This guy we have here. We don't have lambda anywhere in the second equation. And then the rest, like this is this, right? This is this. And this is this. Notice minus signs. Right. So we rewrote everything just in terms of, in terms of matrix vector equations. So here, here, and here. Okay. So it's quite simple, this rearranging of terms. And now we have this differential algebraic equation with variables q and lambda. And we have it in the matrix form. So very convenient, very convenient. Now let us look at this equation. We can actually solve it. We can actually solve it as long as this Schur complement, let me show which one. Like this Schur complement is full rank. So as long as it is full rank, this can be solved. This can be solved. Why? Oh, because the exact solution for this expression would rely basically on Schur complement, and it would rely on also on H being invertible. But H is always invertible because H is a full rank matrix. Because this positive definite, and by the way, the reason this positive definite is because increase in any of the generalized velocities have to increase kinetic energy, That's why it has to be a positive definite instead of positive semi-definite. Yeah, that is the story, right? Now, what we have here is this Schur complement, which if it is full rank, we can invert it, and we get analytical expression for q double dot and lambda. I'm not writing it out here, but those expressions are quite simple. You can find them. We'll maybe have like a whole separate lecture with like we have a lecture on simulation basically, and we'll find the section devoting specifically to those inverses and various problems with them, right? But as long as this is full rank, we could solve this. So this can be solved as long as it is full rank. Now, since H is positive definite, H inverse is also positive definite. So H inverse cannot be negative definite if H is positive definite, right? It cannot be anything else. It has to be positive definite. That is quite interesting. Why, by the way? Well, because this has to do with the fact that eigenvalues of the inverse matrix like has this inverted relation, sorry for punning, with the eigenvalues of the original matrix, and 1 over positive number is still a positive number, so that is why. So H minus 1 is also positive definite. Now, this is a congruence transformation of a positive definite matrix. Congruence means we have multiply the matrix by matrix on the right-hand side and its transpose on the left-hand side. However, it's not a perfect congruence transformation because J is not full rank. If J was full rank, it would have been congruence transformation, and it would have proven that the result is also positive definite. But it is not, because J is in general usually a wide matrix. So it has less rows than it has columns. Wide matrix, okay? Now, as a wide matrix, so it's not, we cannot prove that it is going to give us a positive definite result here. But if J is full row rank, then it would be positive definite. Right? By the way, you can, if you want, you can prove it on your own in your spare time. That is an interesting exercise in linear algebra, in understanding semi-definiteness and ranks. So it's a quite interesting exercise. So if you want, I invite you to prove this on your own. So it will be positive definite, this matrix, if J is full rank. All right. Now, and if this is the case, so if J is full row rank, so the rows are independent, okay? Then the Schur complement works, and we can have a we can have a what do you call it? A invertible and solvable system. So we could, in fact, solve our system, find our q double dot, find our lambda, and everything is great. And we achieve what we set out to achieve. So we achieve the solution of our differential algebraic equation. So, sorry, sounds great. Now, what if J is not full row rank? What if J is not full row rank? That is an interesting question to ask. So, so the row rank of the constraint Jacobian J depends on linear independence of constraints. So if constraints are linearly independent, then everything is fine. It will be full row rank. If they're not linearly independent, we call it over-constrained or over-determined system. For example, if you consider your table as a system with constraints, it will be over-constrained. Why? How do you know? Well, for example, if you replace one of the legs of your table with a wheel, okay? So wheel, something that can, can just slide back and forth, it will still stay still. So one of the constraints didn't actually do anything in terms of determining the position of your table, determining its degrees of freedom. It didn't take any degrees of freedom. In fact, that is one of the ways to compute if the system is over-constrained. If you can take away one of the constraints, and the whole system will still have the same number of degrees of freedom as before, that means that your system is over-constrained, right? And table is very over-constrained. Why? Every single, and it depends on what kind of table you have. If you have like needle-like legs, so very point contact, what we could say, then each leg experiences 2 friction forces, 1 normal reaction force. So there are 3 constraints associated with each leg. 12 constraints overall for a table with 4 legs. But as a rigid body, a table only has 6 degrees of freedom. So 12 constraints, but 6 degrees of freedom. And constraints have this relation with degrees of freedom. We'll discuss it separately. So don't worry if this is, sounds non-intuitive. But each constraint takes away 1 degree of freedom. Okay. So from taking away 6 degrees of freedom could be done with 6 constraints, but your table have 12. And if your legs are not needle-like, so they have a surface, then there are also 3 torques that they generate. But let's leave it. Let's consider that they are small needle-like legs. So in this situation, your table, half of the constraints are excessive, half of the constraints can be taken away. So it is overdetermined. So in this sense, we couldn't compute the inverse of the Lagrange equation for your table, right? But you should suspect that there is a way. And there is a way. So let me explain. So if constraint Jacobian J has linearly dependent rows, so it is not full row rank, then we can define a new constraint Jacobian, JO, okay, as a row space or as a row space basis of J. So a row here is operation that gives us orthonormal basis in the row space of the original matrix. Okay. I think maybe except for, I don't know if there are any of you who feel comfortable with the idea of row space orthonormal basis. I think that's like one of those extremely non-intuitive ideas. But if you feel uncomfortable, you can think of it as a column space basis for the transpose of a J. So J is a wide matrix, right? So let me draw it for you. J is a wide matrix here. Okay. What is the row space? Unclear. All right. Let me transpose it, and now you have here a transpose J. Okay. Now, you can think of column space of this matrix. What is a column space of this matrix? Well, the span of columns of this matrix. So the linear space in which every single column can be housed in, right? Like some linear space in which we have, in which all columns would fit, okay? Smallest dimensional linear space in which all those columns would fit. Span of those columns, if span is more familiar for you. Okay. All right. In this linear space, we can find the orthonormal basis, right? And this orthonormal basis, this is a row space basis for the original one, right? Because all we did, we just flipped it. So before we could say the same thing about the horizontal, like rows, horizontal things. Now we were talking about the vectors in a more familiar vertical term, but it's the same thing. It's the same thing, right? So those two are the same. So we can find this basis in the row space of J, and then we can see that there is a relation between the old Jacobian and the new Jacobian. Okay, the relation is that old Jacobian is equal to some matrix T times new Jacobian. Okay, what is this T? This is just basically just a map that would say how to find each individual row of the new Jacobian given the this orthonormal basis in the row space, right? So each vector in the row, each row of J has coordinates in this row space, right? And those coordinates are would be essentially the let me make sure I don't lie. It would be essentially the rows. Second, it would be rows of tau of T, rows of T. So each row of T is a coordinate is a coordinates of rows of J in this new basis. All right. Again, I think this is highly non-intuitive because of the row space. But if we again think of transposing this whole equation, what we would have is, let me write it here. What we have is J transpose is equal to JO transposed times T transposed. And what you see here is that now each like what they call it column of T transposed is just coordinates in this orthonormal basis GO transposed, which is how we usually think of basis. We multiply it by coordinates and we get a vector. And that's how we get columns of J transposed. So I think here this is a typical way of representing those things, right? Okay. All right. So this is it. And what is also interesting is that in this representation is that if we multiply it by lambda on both cases, on both sides, lambda, okay, we can see that we could propose a new variable, okay, and this new variable, T transpose lambda, we can call it gamma, okay. I call it gamma, is whatever. And notice that this gamma is now multiplied by new Jacobian, which has linearly independent rows. Why? Because is orthonormal basis. So by definition, it is full row rank. And now this would guarantee to have a Schur complement which is invertible. So full rank. So this is invertible now. With this, we couldn't find values of lambda. So values of actual reaction forces would be lost to us. We don't know what's there. But we usually don't care. We usually are interested in tau or in Q double dot, and that we could find. So there is this trade-off. If the system is over-constrained, we can get rid of the get rid of the constraints by finding what we call equivalent representation with fewer constraints, and then we could solve it forward. So this is one of the ways to deal with this type of problem. All right. So today what we saw, today what we saw was Lagrange equations. If you don't remember them, make sure you refresh, right? Lagrange equations, relations between forces and generalized forces, torques in generalized forces, wrenches, generalized forces. Okay. What we also saw is that Lagrange equations can have constraints in them, and the constraints come in as Jacobians, right? As this Jacobian constraint Jacobian transposed times lambda. And the constraint itself looks exactly like in the previous lecture, just some algebraic expression. Okay. So we see that this looks a whole lot like generalized force generated by Cartesian force. Okay. We saw that the same can be done with manipulator equations. We can add to them this constraint Jacobian times lambda and this algebraic expression. Moreover, we saw that the algebraic expression can be differentiated twice, right? Like this and like this, to get to a form of manipulated equation where we would have explicit second order derivatives in both the differential equation and what used to be algebraic constraint, but now it is a differential constraint. So now, in a sense, if you ask me, is this ODE or is this a differential algebraic equation? The only way I can answer that this is differential algebraic equation is because we still have lambda here. Okay, we still have lambda here. If it wasn't for this lambda, we couldn't even say what it was. Next, we could express it in this matrix vector form, and we can solve it if the Schur complement is full rank. If Schur complement is full rank. And what we also saw is that Schur complement can be made into full rank if it isn't by this trick. So ultimately, mechanical systems tend to be deterministic. So you could always determine the accelerations if you know initial conditions. So almost always there is some way to solve for the next stage, like solve forward a mechanical system, like expressed as differential equation. Reaction forces are deterministic, but in a different way. In the real world, reaction forces are essentially a product of interactions of smaller subsystems. So, for example, reaction force that comes from the ground is best described by the partial differential equations that describe the elasticity of the ground, right? You can think of the ground as an elastic substance, like for example, if the ground is made out of wood, you have this wood that like a wood beam that kind of like is, how should I put it, deforms under your weight, produces some reaction force. This is described by partial differential equations. In general, this is way outside of the course of mechanics and way outside of the course of robotics, how to accurately model reaction forces. And with that, we in robotics, we usually think of reaction forces as, how should I put it? We think of them as a product of working with these equations rather than thinking about them as the product of accurately modeling underlying physics. In fact, for us, it is usually not quite so important to understand exact nature or exact value of reaction forces. Accelerations is a completely different matter, though. Accelerations for us is very important. So here I would like to close with this, one thought, right? We know how to we know how to describe systems with constraints, using Lagrange, using manipulator equations, right? And we know how to find Q double dot. That is something that you can always expect to find. With the finding reaction forces, it is not always as straightforward. And this theme will come back to it at least a few more times during the course. So is quite a subtlety, I guess, with the contact over control. Yeah, the reaction forces have everything to do with contact. You have to be aware of them, and it's not always straightforward how to find them. Right? Do we have any questions? If not, then we'll see each other next week. And good luck with your practical session. See you later, guys.
Thank you, Professor. Goodbye.
Thank
Bye.
you, Professor. Bye.
Why don't we meet for the next week?
No, we will have a course
okay.
next week, of course.
Okay, sorry. Good
No,
yeah, okay.
good question. Good question. All right. See.